Good morning, friends. Myself, Professor Prashant Mahajan, working as an assistant professor at AISSMS Institute of Information Technology. So, in the previous two lectures, we have seen instrumental methods of analysis, and in that, we have seen electrochemistry and types of electrodes. So, today we are going to start new topic, that is conductometry. So, what is conductometry? So, conductometry deals with the measurement of the electrical conductance of an electrolyte solution such as acid, base, and salts. These solutions conducts to movement of ion towards opposite charge electrodes. Conductometry is used in neutralization titration, precipitation titration, chemical kinetics, and plant laboratories. What is conductometry then? That means if we are going to consider NaCl solution, in that solution, that cations present in the NaCl, that is Na plus, will move to the cathode, that is negatively charged. And in the case of Cl minus, that will be negatively charged, so that will move to the positively charged anode. So that is called as conductivity. So in that we are going to see Ohm's law, then conductance, then specific conductance, specific resistance, cell constant, molar conductance, equivalent conductance, and factors affecting conductance. So first, Ohm's law. So as you know from the 12th, the Ohm's law is the current flowing through a conductor is directly proportional to the potential difference applied across the conductor and is inversely proportional to the resistance of the conductors. So that is I is directly proportional to the V. When we remove that directly proportional sign, that will become I is equal to V upon R. So I is current in ampere, V is potential difference in volts, and R is resistance in ohm. So that is called as Ohm's law. So next is conductance. So conductance, the definition, first of all the symbol is capital C. So the definition is the is with which current flows through the conductor of the solution. Conductor or solution. It is reciprocal of resistance, that is C is equal to 1 upon R. So C is, its unit is per ohm, that is also called as mho, that is also called as Siemens. So that is conductance. Then next is specific resistance. So specific resistance means what? This is specific for this cell. That means what? The ions present in this solution, sorry, in this cell are specific. That means that cell, it is that two electrodes are separated from each other by L centimeter, which is having area, that is A. So you can see resistance of any uniform conductor R is directly proportional to the length L and inversely proportional to the area of cross section. That is R is directly proportional to L by A. That is, when we remove that proportionality sign, that will become R is equal to rho L by A. So we want rho, this rho. So rho will be become RA by L. So that is rho is equal to RA by L. So that unit will become, this is ohm, this is centimeter square, and this is centimeter. So this centimeter and this centimeter get cancelled, and that will become ohm dot centimeter. So when L is the length, A is the area. So that is your specific resistance. Next is specific conductance. So that is specific conductance. It is the reciprocal of specific resistance. So it is denoted by K. So K is 1 upon rho, and rho value is RA upon L. So 1 upon RA by L. So that L will go to the upper side, and the unit will become, its unit is ohm dot centimeter. So its inverse will be per ohm per centimeter. So you can see K is equal to L upon R into A. So the unit of length is centimeter, the unit of resistance is ohm, and the unit of area is centimeter square. So upon doing the calculation, you will get this unit per ohm per centimeter. So next is cell constant. So cell constant is the ratio of length upon area in the equation is known as cell constant. So it is constant for given cell, that is L by A. Its unit is centimeter inverse. So the formula becomes specific conductance is equal to measure conductance into cell constant. So I am talking about this. Specific conductance is equal to 1 upon R is observed conductance and L by A is cell constant. You can see specific conductance, that is K. Cell constant is L by A, and 1 upon R is observed conductance. So the formula will become cell specific conductance is equal to measure conductance, that is observed conductance, into cell constant. Then next is equivalent conductance. So to understand that the meaning of equivalent conductance, imagine a rectangular truck with two opposite sides made of metallical conductor acting as electrode exactly 1 centimeter apart. If 1 centimeter cube, that is 1 ml solution containing 1 gram equivalent of an electrolyte is placed in this container is measured. That means that concentration of that solution is measured in gram equivalent per centimeter cube. Then that conductance is called as equivalent conductance. So V is the ml of solution containing 1 gram equivalent of electrolyte. So simply you have to remember, if the concentration of the solution is C gram per liter, gram equivalent per liter, then the volume containing 1 gram equivalent of the electrolyte will be 1000 upon C. So lambda is given by K into V. So V is nothing but 1000 by C. So K into 1000 divided by C. So unit of specific conductance is per ohm per centimeter. Then 1000, that is centimeter cube, and concentration is gram dot gram equivalent. So upon doing the calculation, you will get final unit as per ohm centimeter square per equivalent, that is equivalent conductance. So how to remember? The concentration, it is given in gram equivalent per liter, that is called as equivalent conductance. And next is molar conductance. In that case, the concentration is given gram per mole. So you can see the molar conductance is defined as the conductance of all ions produced by ionization of 1 gram mole of an electrolyte when present in V ml of solution, which is denoted by mu. So molar conductance is mu, that is K into V. So K into 1000 divided by M. So this M is molar concentration. In that previous case, that C is gram equivalent concentration. So where V is the volume in ml containing 1 gram mole of the electrolyte. If C is concentration of the solution in gram mole per liter, then the unit will become per ohm centimeter square per mole. So that is the seventh term, that is molar concentration. Then next is measurement of electrolytic conductance. So for that we have to use Whitson network bridge that you have already seen in the 12th. So first you have to calculate the resistance of the cell, and then you have to take the inverse, that will be the conductance of the cell, that you know very well. So this is the diagram of Whitson network bridge, that is plus charge is connected to the A point and minus charge is connected to the C point. So we can say that the potential difference at EB is equal to the potential difference at ED. So that is nothing but this one, I1 R1 is equal to I2 R2. Similarly, this is I1 R3 is equal to I2 Rx. So these are the terms. So this potential difference is equal to this potential difference. Then this one is equal to this one. Upon dividing, you will get this formula. That is Rx is equal to R2 into R3 upon R1. So this is Wheatstone network bridge method. The next is conductivity cell. So you can see here. So this is the second apparatus for measuring the conductance. So S is there, source. C is resistance of the cell. Galvanometer is there. RS is the shunt resistance. So you can see RC upon RS is equal to AX upon BX. So we are going to see we are going to move this pointer till the galvanometer shows null deflection. When it shows null deflection, we are going to note that value. So we know if suppose AB is 10, AX is 6, we will get BX as 4. So we are going to calculate resistance of that cell. That is one more method. And last, that is factors affecting conductance. So there are four factors. First, concentration. So as concentration increases, conductance decreases. So just remember, conductance is depend on the mobility of the solution. That means as dilution increases, conductance of the solution increases. In the opposite way, as concentration increases, conductance decreases. Second, size of the ions. Smaller the size, greater is the mobility. For example, you can consider H plus, Na plus, and Li plus. So all are having same charge. So H plus is having small size, so it will move faster than Li plus than Na plus. So that is size of the ions. That means smaller the size, greater is the mobility, and greater is the conductivity. The next is charge on the ion. So greater is the charge, greater will be the conductivity. You can consider the example of Na plus, Mg plus 2, Al plus 3. So that is all are having same size. You can see Na plus, Mg plus 2 and Al plus 3 are having neon configuration. So Al plus 3 is having more charge, so it will move faster than Mg plus 2 and Na plus 2. And last, that is temperature. So higher the temperature, higher will be the higher the temperature, ion will gain kinetic energy and it will move faster. Hence, higher will be the conductivity. So at higher temperature, kinetic energy of ions are more. So you can see there are four factors. The first one is concentration. So concentration is inversely proportional to the conductance. Second is size. That is smaller the size, greater is the mobility and conductivity. The next is charge. Higher the charge, higher will be the conductivity. Temperature. Higher the temperature, higher will be the kinetic energy, higher will be the mobility, hence higher will be the conductivity. So that is from the today's lecture. Thank you.